Hello students, welcome to this video lesson. I'm trying to make myself a little smaller here because I don't need to be too big and take up too much of the space. So I'm not having any luck making myself any diagonally smaller here. Sorry, okay, so we'll leave it at that. Okay, so welcome again. So this video lesson is going to talk to you about the differences between mass and weight, which you've often thought interchangeably. If somebody says, I'm going to go weigh myself on a set of scales. Well, you are weighing yourself, and we usually measure things in pounds, which is actually, it is a mass, but that's not actually weight. We're going to learn today that there is a difference, even though it was often used interchangeably. All right, so I'm going to first throw up a cartoon here. I have a couple of cartoons I want you to take a look at. And so these young people are playing soccer and pondering physics. And so the first boy says, adding air won't affect the weight of a ball. Air is just empty space. Another young child says, if you add air, the ball will weigh more because air is made of atoms and they have mass. Another young, like a girl here, says, adding air to my ball will help it bounce higher because it will be lighter. Air makes things lose weight. And finally, what do you think? So, are any of these folks right? Maybe they're all right. And maybe at some point I will ask you to tell me who you think is right and who is wrong. Next slide. This is a gravity cartoon that I found, and so we'll go around the circle here, and down here in the bottom left, gravity pulls on things on Earth, but not in space. Astronauts float. And young man with glasses here. Gravity pulls things to the center of the Earth. And I can tell this is British because they've spelled center with it. Centre. I can tell this is probably European British. Upper right, gravity only pulls on things that are falling. So it's only pulling on things that are falling. Gravity pulls on things and makes them fall down. So any of those right? All of them right? Are any of them wrong? And again, we'll come back to these at some point and we'll talk about these. So the targets for today, and I do wish I could make myself smaller because I don't want my screen to have to be so big, but oh well, any doubt. So the targets today differentiate between weight and mass, and then apply Newton's second law to determine unknown variables. So you've actually already talked about Newton's second law. Newton's second law helped us to figure out how fast something was going if we applied a force to it. So we've talked about Newton's second law, but we never put it in terms of weight and mass yet. That's what we're going to do today. So I would encourage you, if you feel that you want to write any of these things down, if they're new to you, feels like it's important. There won't be a lot of content here, and I will have some slides to talk about, or some problems that will work along with this lesson. So this is a graphic that's comparing mass and weight. And so we see mass here. Mass is measured in kilograms, so we've seen that kilograms. Kilograms is about 2.2 pounds. So so that means that actually I should say this, 1 pound is 2.2 kilograms. 1 pound, did I say that right? No. Yes. No, the other way around. 2.2 kilograms, 2.2 pounds. Mr. Eckert, end of the day here, I'm a little bit brain dead. 2.2 pounds is 1 kilogram. So if a good thing is kind of cut things in half. So if you have 100-pound bag of feed, if you divide that in half, it's about 50 kilograms. That's about the going rate. It's not exactly that, but that's kind of ballpark. Whereas we're going to measure weight in newtons. We're going to measure weight in newtons. Mass doesn't change. Unless you lose weight or something. But even then, when we lose weight, we're really losing mass. No matter what planet we go to, we're going to have the same mass. We have the same stuff. Stuff is really the matter. Mass is matter. Whereas when we change location, weight's going to change. So different planets will have different weight. So mass is closely related to inertia. Now, what we mean by that, inertia is something wanting to stay in place. So if you've ever seen the famous experiment where somebody takes something and they pull it out from under like a tablecloth and they pull out the tablecloth and all the plates and things are sitting on there, the really heavy things will stay still. The lighter things actually move more easily. So as it turns out, the more massive things are, the more inertia. Inertia is really the resistance to motion. So really heavy things want to stay still. Plus, really heavy things want to stay moving. We might say momentum. If something really heavy is moving, we might actually say that's lots of momentum. It wants to keep moving forward, but it really has a lot of inertia. And it's also why something that's spinning really fast will want to continue spinning because it has what's called rotational inertia. So inertia is really that idea of something wanting to stay in rest or in motion, whereas weight, we don't discuss it in those terms. We just say that it's closely related to gravity. In fact, it's directly proportional. If we double gravity, we double weight. If we have gravity, we have the weight, Halves, if we have it, which is really weird because we have gravity, but if we half it, if we cut it in half, I should say, then we would half the weight. And then we cannot directly measure, we cannot really directly measure the amount of mass. We could kind of do that by maybe a density and a volume. We could calculate mass. But as far as measuring it, it's really tough to do. But however, in weight, we can really do that using a scale. And we'll see that today, how we actually go about that. All right, so now as far as quantifying that, and here again, I'm kind of in the road here. So quantifying it, we have a really simple formula. And again, we've seen this. This should look familiar to you. But we're going to throw a subscript in here and say force sub W, the force of weight, is equal to mass times gravity. And this you will have. And in fact, you've been given this document. And so that formula is down here for you to have. Please don't write on this. You'll be able to use this on assessments. It says that over towards the top. Now, I almost forgot on this last graphic. Down here in the bottom right-hand corner, I have this little cartoon that I pulled in here. That's more of a graphic, not really a cartoon this time. My weight on Earth is around 560 newtons. That means that person weighs about 56 kilograms. Well, I'm a little more than 56 kilograms. On the moon, this person has a weight of 90 newtons. Now, why is that? Because the moon, is pulling with less force. It has less gravity. But no matter whether we're on the moon or whether we're on Earth, the mass is still the same. The mass would be 56 kilograms. Okay? All right, so so we talked about this slide and gave you that equation there. And so really weight is a force. Force is something that can do work. It can move an object. It doesn't necessarily have to move an object. I can push and I can push on this desk and it's not going to go anywhere. In fact, if I pick up my feet and I push, the desk doesn't go anywhere, but I go back because this desk actually pushes back on me. And that's Newton's third law of equal and opposite forces. And the reason I moved back is because I was pushing with a certain amount of force, but the friction of my wheels wouldn't let me stay still. So the table, I didn't do it. The table actually pushed me backwards. It's kind of a weird way to think about it. You might say, well, Mr. Hacker, you were applying the force. Well, I was applying a force that wasn't balanced and I got pushed backwards. So we'll talk more about Newton's third law in the next lesson, actually, when we talk about net forces. Now, I do want to talk just really briefly. Actually, you know what? I'm going to ask you a few questions that will kind of summarize these things, and then I'll talk about the table next. So I'm just gonna go like this so that I'll know that I need to come back and split the video right here. All right, so I'm back, and I'm going to move me off to the side. I'm probably going to disappear for a moment because I'm going to cut this out when I'm doing my capture. So don't worry about things. Now you have this chart to look at. But I want us to look at this just a little bit. I think it's some interesting data here. Nothing to memorize, just some interesting maybe nuggets of information. Nothing here maybe is earth-shattering. This is showing us the heavenly bodies of the planets, except for Pluto. Pluto still is not a planet. It is a dwarf planet, and we'll kind of see why in a moment. It doesn't have there's a couple reasons it's a dwarf planet. And it's not necessarily because it's so small, although it's dinky. It's mostly a dwarf planet also because it has a very irregular shape, and it's actually not in the same plane as all the other planets. All the other planets are in the same plane. Pluto's is kind of it's very elliptical. In fact, sometimes Pluto is inside of Neptune, and sometimes it's outside of Neptune. So it's always not always the furthest planet as well. So it's a weird shaped orbit. Um, but if we look at things and we look at the mass, when we look at and this is in something times 10 to the 24th kilograms, whatever that number is, ginormous number, and it probably has a name. But so the mass isn't that important to me, except we'll come back to that. Diameters, not necessarily overly important. We can tell Jupiter is the biggest, Saturn is the next biggest, and we can even tell, like if we put Earth, so Earth is 12,756 kilometers. Jupiter is 142,000, almost 143. So if I take my fancy calculator and I do 100 and I turn it on, 143,000, yes, divided by the Earth's diameter. So Earth's diameter is 17 or 12,756, 11. So we could actually fit 11, there it is, 11.2 Earths across Jupiter. It's ginormous. It's big. And so you get the idea. Now our moon, and our moon is, if we look at the diameter of our moon, 3,500 kilometers is the diameter. That would put it about 3 or 4 of them across Earth. So if we would think of the moon compared to Earth and the Earth compared to Jupiter, the moon is much more similar to Earth in size than what Jupiter. Jupiter is massive, and it is gas. It's pretty solid and pretty dense. Actually, we'll see that in just a moment. I wouldn't say solid, but it's pretty dense. Now, speaking of density, I think the density ones are actually pretty interesting. If we could take the planets and we could like pluck them out of their orbits around the sun. I actually should have put sun on here as well, but sun is even size. We can't even imagine the size of the sun. Actually, it's big. The densities are interesting to me. If we could take it and we could like put them in a big ocean and see them float, some of them would float and some of them actually, well, at least one of them would not. Now, this density that we have here, this kilograms per meter cubed, so this, for instance, is 5,427 kilograms per meter cubed. Now, what does that mean density-wise? Well, let's think of water. Water would have a density of 1,000 kilograms per cubic meter. So if we had a cubic meter, so a cubic meter of water, and I know I'm out of the frame here, so like, a meter by a meter by a meter, that would be 1,000 kilograms. Water's really heavy. You think about 8 pounds for a gallon of water. But so this gives us some reference. And so if we look at the density of these, there is a planet that would actually sink, or all these would float. So Mercury, Venus, Earth, Moon, Mars, even Jupiter would float, or excuse me, sink. It would sink, even though it's a gas giant. It's super condensed. Overall, it still has a density that's greater than 1,000, so it would actually sink. However, Saturn, that one, even though it is also a gas giant, it would actually float because it has a density less than that 1,000 of water. And so I think that's kind of an interesting. There's a fun fact for you. In fact, I might throw that up on fun fact on Schoology. But so yeah, Saturn would float if we put it in water, if we had a big enough ocean. Now, what's most important for us here are the gravity values. If we look at the gravity values, and this is why we really want to keep this sheet around, are for those gravities. And so these are the gravities that we will use moving forward. So even Earth, let's make it 9.8, and let's also not let these change our sig figs at all. So we'll just kind of assume these are precise measurements, even though we know Earth is like 9.81. Technically, Earth at sea level is 9.07. Something, so it goes on for a while. Escape velocity we may talk about later. This is the velocity that something needs to be just at in order to orbit, or to escape the Earth's gravity or the Moon's gravity or whatever it might be. So again, we'll talk about that when we talk about some terminal velocity. So, and my phone is ringing here, so give me just a moment. I'll be right back. All right, so I'm back there. I had a phone call. But again, kind of keep this information around. Now, what the remainder of this is, hopefully now you've got this idea between mass and force, or excuse me, mass and weight. Weight being a force, mass is just the amount of matter that's there, measured in kilograms. If I take this calculator to Mars, it's going to have the same mass. So if I figure out the mass of this, now how would I figure out the mass of this? Well, I could actually use a pan balance, and if I have some masses that I know are exactly 100 kilograms, so if I could actually use, so if I have one right here, I happen to have a balance, and I could actually figure out if I put my calculator on one side and I had masses like 100 grams and 200 grams, and I made this exactly balanced, I wouldn't know the amount of mass. Now we can calculate it, and that's what we're going to do in some of these problems that come up in the next set here. The rest of the questions on this assignment will be a series of questions. So it's going to give you a slide, maybe. It'll give you a slide to work. Use calculator, use that base formula. We really have one formula to use. Use the gravity values that are supplied on here. Then what I will do is once you answer it, then I'll have a slide of me working it. So I've already worked the problems. I've got those here. So you'll see the slide after that will be the problem worked. I won't talk anymore. I'll just presume I'm going to guess you can figure it out from my work that you'll see. So, all right. Thanks for watching this, everybody. Do your best on these. There are about 5 or 6 problems there are. I will see you next time.